Excited to share this joint work with you, joint with my advisor, Dr. Braun, and our other research collaborators, the latter two of whom are optometrists at Indiana University. And I'm going to share with you today my work on fitting human tear film data with mathematical models to understand what causes tear film thinning and breakup. So to jump in, the big question that I want to leave you with an answer to today is, what can math tell you about the water on your eyes? If you're not a math person, you're probably wondering, what is she even going to hope to be able to do? And hopefully you can take something away from this. So I'm going to jump in with some background. First is, what is the human tear film? So the tear film is a 3-layered film. The 3 layers are shown here. So this is your eye. So it's a really thin layer right on top of your eye. The largest layer is the aqueous layer made up of mostly water. There's a thin, oily lipid layer on top that, when correctly organized, is a good barrier to evaporation. And there's a mucin layer here that sits right on the cornea or the eye. And our main motivation for studying the tear film is for the applications in dry eye syndrome, which I'll get into in a moment. So the main topic of this talk is the phrase tear film breakup. So we need to understand what that is. So simply put, it is any thinned region in the tear film. So optometrists instill the molecule sodium fluorescein into patients' eyes and then image them in order to see characteristics of these thinned regions, such as how fast they form and what shape they are. So these highlighted regions in this video here are breakup. This is the upper eyelid of the tear film, or of the eye. The lower lid is down here. This is the white of the eye on the sides. Our focus is in this middle region called the cornea. And that is where we're looking for breakup, and it appears as these dark regions. There are other dark regions in this person's tear film, you may notice, but I've just highlighted a couple. And the big question that we want to answer is, what is happening in those breakup regions, the regions where the water has thinned over time? Maybe the tear film is very salty there. Maybe the eye has become inflamed. But the truth of the matter is, there is really no way to answer those types of questions except through mathematical modeling. So that is where we're trying to use math to learn something about what's going on with the water on your eye. So now that we know what tear film breakup is, we can answer the question, what is dry eye syndrome? So depending on diagnostic criterion, this is a condition that affects up to half of the population. So it is pretty prevalent. And simply put, it is a condition where the eyelids and the tear film aren't protecting the eye. So it's characterized by several things, including tear film breakup, which we just described, very salty tears, or a condition that's called hyperosmolarity, which I mentioned as a question before, and also inflammation. Okay. We're going to be focusing on the first two today. How do you treat dry eye? Unfortunately, you take a try and try again approach if you are an optometrist. So at the start, an optometrist might ask you to change your diet, add in anti-inflammatory foods, or they might suggest using artificial tears. If that doesn't work, you move down the steps of the ladder and keep trying things again and again. And on the very bottom rung, if nothing else has worked, you might try this thing called an amniotic membrane, which has been described to me as a Band-Aid for the tear film. And I wear contacts, and so I'm very used to touching my eye, but this sounds terrible. So you don't want to get down the rungs of the ladder all the way to something like this. So the problem is that these treatments, these variety of treatments, aren't really addressing the underlying causes or the mechanisms that are causing this dry eye syndrome. And those are evaporation and lipid dysfunction. And those are what we're going to address with our modeling efforts. So I just mentioned them. We're going to do a little bit more about them. So the first tear film breakup mechanism we're going to look at is evaporation. It occurs in a relatively slow time frame, so a breakup region would take over 8 seconds to form if evaporation is the mechanism causing it. The other one we're going to look at is lipid dysfunction, and specifically Marangoni flow, or this concept called the Marangoni effect. And this is driving very rapid thinning, something that occurs in under a second. So evaporation, most people can understand, but this Marangoni flow is harder to visualize. So I've got a little video here that is going to help explain the Marangoni effect. On the left here, I've got 2 Petri dishes. On the left is pure water, on the right is soap, and we are adding pepper flakes just to show fluid movement. The Marangoni effect is all about changes in surface tension. The soap has a lower surface tension than the water, so when you add a drop to it, it induces this dragging tangential flow, and you can see from the pepper flakes that the water is shooting out to the sides. So when you think of the Marangoni effect or Marangoni flow, think of really rapid tangential flow. Okay. And again, it's driven by this change in surface tension. So that brings me to build our mathematical model. To start the modeling process, we always start with our goals. So we have 2 main goals here. The first is to model the mechanisms causing tear film thinning and breakup. The second is to estimate related breakup parameters that can't currently be measured by optometrists. So take us back to that question that I had about what's going on in breakup. Can we say something about how salty the tear film is, for example? Okay. So to model tear film, the model itself is built on a fluid mechanics background, and it considers both evaporation and the Marangoni flow either separately or in combination. We are currently applying the models to healthy patient data, people who do not have dry eye syndrome, and this is in a basic science framework. And so if we understand what's going on for healthy patients, that might give us a baseline to then compare to people with dry eye syndrome. All right, so I'm going to build the model here. So in this picture on the left, you have to pretend you're standing on top of the cornea and you're looking through the tear film. Okay, so you're seeing this breakup region form. Up here is the air, all of the blue is the tear film, and this yellow is the cornea. So this white space here is where that breakup region is actually forming. So the model tells us how a couple different things change over time and in space. So the tear film height, which is this black line, so it's low right in the middle of breakup, depends on a couple things. Evaporation is drawing water out from the tear film, so it's decreasing the tear film height. Osmosis is adding fluid from the cornea to the tear film. We know osmosis moves water from regions of low concentration to high concentration. So the tear film's getting salty, so it's high concentration, so you're moving pure water from the cornea into the tear film, so it's adding to the tear film height. And there's inward pressure flow trying to fill in the breakup region, so it's bringing water into the breakup region and increasing the tear film height. So kind of competing things going on. This fluid pressure itself is based on the curvature of the tear film, and they're negatively related. So when the tear film is concave up, right, it looks like a smiley face here, that means the pressure is negative, and that tells you the direction, it's inward. Finally, we can talk about how the concentration of salt and fluorescein change. So the salt moving around, the fluorescein is the dye that the optometrists have instilled in order to image the tear film. So first of all, they're affected by evaporation. So evaporation is taking water away from the tear film, so it's concentrating the tear film. So it's increasing those concentrations. Osmosis is diluting the tear film by adding water, so it's decreasing those concentrations. And then advection moves with fluid flow, so it's bringing those solutes into the middle. And diffusion spreads things out. So they're highly concentrated right in the middle of the breakup region. So diffusion is going to move things away. So it's going to spread things out. So without any equations, this is the gist of the evaporation side of things, the evaporation model, what's going on in the tear film itself. So that's the first mechanism. Now we're going to add in the next one, which is the Marangoni effect due to lipid dysfunction. Okay, so to start our lipid dysfunction model, we now have some lipid sitting on top of the tear film. So think of this lipid glob as that drop of soap that's being added. So it's going to induce this rapid outward tangential flow and start creating a breakup region. Okay. The lipid itself, outside the glob, so out here, depends on a couple things. So advection, because the Marangoni flow is moving outward, it's advecting the lipid also outward, okay, so spreading out, and diffusing outward, again, going from high concentration to low concentration. So that's moving outward as well. The overall fluid flow we introduced before pressure flow, but now we have this lipid-induced flow. So we'll talk about the overall fluid flow, which is a combination of those two. So as we mentioned, pressure flow is inward. Marangoni flow, very rapid, very strong, and that is outward. So this builds our model. First one tells you about a lot of things going on in the tear film based on evaporation. This one tells you about the lipid itself and what it does to the tear film, right? So that builds our model. Again, no scary math equations. How do we compare these models to experiment though? I have these images that have pixel values, right? They have pixel intensity values. And it just showed me a bunch of models for things like tear film height and lipid concentration. How do I match those up? So, yep, we have all these models for our different quantities. And we can solve these numerically. We choose to do so in MATLAB. And then we take the solutions for the tear film height and fluorescein concentration, and we plug them into this handy dandy formula for a theoretical fluorescent intensity. Okay, you can see where tear film thickness H, fluorescein concentration F show up. So we have experimental fluorescent intensity from our images. We now have a theoretical fluorescent intensity from our model, and now we can compare the two. Okay, so now I'm going to describe how we do that comparison. All right, so let's look at some examples. So let's go back and talk about how things are differentiated based on mechanism and speed. So we mentioned before, evaporation drives pretty slow thinning. So let's watch a movie, and you can focus on this circle region here. I'm going to be looking at this circular breakup region. I should mention here, our models are designed specifically to capture either very circular breakup or very linear breakup. Okay, and that's due to the geometry in the model. Okay, so we're going to be looking at this spot. So let's fit the model to the image data. All right, so here's our picture again. There's a lot of pre-processing that goes on. There's a stabilization or registration process. We need to align the images because people's eyes move, and we turn them to grayscale. We filter them to hopefully deal with some noise. And once we're done with that, we identify a breakup region. Okay, so this is the one that I looked at in the movie. We have a way, and this is actually kind of exciting. I'll pause here for a minute. This we developed just in order to do our process here, but as a side note, being able to estimate something like an initial tear film height is very useful to eye doctors. So although it's just a part of our process, this could be something that could be of use in the clinic. All right, so now I'm going to extract experimental data across this line of breakup that I've drawn over the breakup region, and I'm going to do so from every time level. So these are the different times. It's going down. And here's the spatial variable. So You can see the breakup region forming in time, and you can see what it looks like across the breakup region also. Okay. Then we're going to minimize the difference of the experimental fluorescent intensity from the images and the theoretical fluorescent intensity from our model. And what we're going to do is we have a couple parameters that we're going to vary until we get the best fit possible. We get the best match of this on top of this, right? As closely as we can. So the parameters that we're going to adjust are related to our evaporation distribution. So we have a peak evaporation rate, how fast breakup is forming in the middle. A background evaporation rate, how fast things are evaporating on the sides. And a width of our distribution. So it's a Gaussian. If you've heard of a bell curve, that's essentially a Gaussian. Okay. This gives us a sense for how large our breakup region is. So we're going to vary these three parameters until we find the values that give us the best fit, the best overlap of the theory with the experiment. Okay. So let's look at our results. So on top here, we have fluorescent intensity. The dashed lines are the theory, and the solid lines are experiment, and the same colors correspond to the same time levels. Okay, so you can see it going down in time. So what are some takeaways here? Here's our tear film height profile as well. Well, if you look at the tear film height, it only drops by 45% in the center of breakup, so we don't have very significant thinning. Another thing, if you look, if we compare our results with some point measurements, we can get a sense for whether our values are physically relevant. So this data from this paper is given here in red, and they were only looking at overall thinning rates of the center of the cornea. Okay, they were not looking for breakup in particular, and they could not separate evaporation from the other effects. So here's our peak evaporation rate and our minimum evaporation rate. And they're close to this distribution, but I mentioned they're not an overall thinning rate. So our overall thinning rate falls very solidly within this distribution. So that's a good check that our procedure can find physically relevant quantities. Okay. Also, because that overall thinning is slower than the peak evaporation rate, it's an indicator of inward flow. And we know that pressure flow is always inward. Marangoni flow is outward, but this fit is just done with the evaporation model because it's a relatively slow breakup region. All right, so I mentioned Marangoni effect. Let's look at an example where that's involved. So I'm going to play this video again if I can, because it's kind of fast and kind of interesting. You'll notice I start with the person's upper eyelid covering the breakup region. So we had to find a way to deal with that, but this spot is the one that I'm going to focus on. So the setup for comparing the combination model with data, and again, here I've got both evaporation and the Marangoni effect. Think again of that glob of lipid causing thinning together. So we're going to compare this model to the data. Similar start, we're going to identify a breakup region. We're going to extract data across the breakup region from every time level. Again, we're going to minimize the difference of the experimental fluorescent intensity from the images and a theoretical fluorescent intensity from our model over slightly different parameters this time. We have a single evaporation rate. We have the size of the glob of lipid. And we have a number quantifying the strength of the Marangoni effect. So here we're using a different evaporation distribution. You might remember from the beginning, I mentioned the organization of the lipid layer is important. If it's well organized, it provides a good barrier to evaporation. But a glob of lipid, we hypothesize, is not very well organized. And so it's doing a very poor job of providing a barrier to evaporation. So outside the glob, a good barrier, no evaporation. Under the glob, disorganized, evaporation's getting through. Okay. So let's look at the results of fitting this model with these parameters. Again, we're varying these parameters until we get the best match of theory and experiment. Again, we have fluorescent intensity on top, okay, tear film thickness on the bottom, and something you might be noticing, let me mention again, the combination means both evaporation and the Marangoni effect. Okay. These magenta time levels might be jumping out at you. So as you noticed in the video that I pointed out, the person's upper lid is obscuring the breakup region as it's forming at the beginning. So thinning has already started before we can even see in the data. So we added these magenta time levels just to get our model going, and then we started comparing with experiment. So again, solid curves are experiment, dashed curves are theory, same colors are the same time levels. Okay, so you can see very good agreement over time. So what are some takeaways from this instance? Well, if we look at our film thickness profile, we have a significant drop in thickness in contrast to the previous example, 95% drop. If we compare our evaporation rate to these point measurements, it falls solidly within the distribution, okay? But if you remember, these red data points here just targeted the center of breakup and only looked at an overall thinning rate. So we need to look at our overall thinning rate in comparison. Again, it falls nicely within their distribution, so a good check that we're finding physically relevant quantities. And our overall thinning is faster than the evaporation rate due to outward flow. So evaporation is decreasing the tear film height, and outward flow is decreasing the tear film height. Okay, and this is characteristic of very strong Marangoni flow, beating the inward small pressure flow. Right. So let's look at some things kind of together and try to answer an important question. How can we tell which mechanism is causing the tear film breakup? There's a couple things we can look at. One question we can ask ourselves to answer that question is flow inward or outward? So if flow is inward, it's slowing thinning, and we know that evaporation is the dominant mechanism because it's only pressure flow that's winning. Right? The Marangoni flow is too weak, and the pressure flow is taken over, and that's characteristic of evaporation-dominated thinning. In contrast, if the flow is outward and strong, it's speeding up thinning, which we know goes with the rapid thinning of the Marangoni effect. So if the flow is outward overall, Marangoni flow is beating the pressure flow, and it's causing this fast thinning. The Marangoni effect is going to be the dominant mechanism. So the flow direction is a really quick check for us to say which mechanism is causing the thinning. It's inward, evaporation. It's outward, Marangoni effect. All right, what's another thing we can look at? We can look at how fast the tear film is thinning. Right? Evaporation, we think, is a relatively slow process. Marangoni effect, pretty rapid thinning. So the first thing I'm going to pause and point out here is that if we look at evaporation rates, we can separate evaporation from overall thinning. This couldn't be done before, right? In looking at patient data. They can only get an overall thinning rate. So these first two here are from our evaporation-only model. The second is from our combination model. But the thing that's really important to look at that we can compare again with data is our overall thinning rates. So first of all, if we look at our results together, we have very good agreement with experimental values, right? We're only off a little bit, and we do expect our values to be faster because we're targeting breakup regions. Our evaporation results are in blue. Combination model results are in red. And again, reminding you, this includes the Marangoni effect driven by the lipid club. And apart from this outlier here, we have really good separation of these two results. So if you exclude the Marangoni effect, well, you get slower thinning, right? And if you add it back in, you get faster thinning. So this again provides a way to suggest which mechanism is causing or at least involved with the thinning. And then something that I'm going to return to, we talked about wanting to know something about the saltiness of the tear film. Well, this is a really big deal to clinicians. Why is that? Because measuring the salt level in the eye is part of how they diagnose dry eye syndrome. Currently, they can only do it near the lower eyelid. But we can measure it in tear film breakup. And tear film breakup leads to dry eye syndrome. So you'd think you'd want to be able to measure this in tear film breakup. Right? So this is a big deal. So here's our results. We've got the combination model with evaporation and the Marangoni effect, and our evaporation only model. For reference, you can see our scale of salt concentration on the y-axis here goes up to about 900. We have one data point approaching that. Seawater is about 1,000. So our largest data point here is approaching seawater concentration. That's a very salty tear film. What can we say? So first of all, if we look at the cases that have the Marangoni effect included, it's interesting and wasn't thought before, they can still have a pretty high salt level. We still see an increase to about 700 milliosmoles in about 4 seconds. Also, except for this one outlier, a lot of our values, regardless of the length of time of the trial, are leveling off. And one way to explain that may be that diffusion is just able to move the salt concentration out of the breakup region, okay? And so it never increases beyond that value. So we may have kind of debunked a theory here which said that if the trial is longer, it's just going to continue to get saltier and saltier and saltier. And our results just don't show that. So this is some new and exciting information. All right, to wrap up here, I've got some new results. Let me mention these are new and hopefully exciting, using a very hot topic right now, machine learning. So we have a team that's been working for about a year, over a year now, and trying to, first of all, automate the detection of the breakup regions. So we're following a paper by these authors, Su et al. And what we did was we were classifying these little squares that we call image patches. And we're trying to determine what's going on in the cornea in that little square. Is it an eyelash? Is it tear film breakup? Is it not tear film breakup? Is it the white of the eye or the sclera? Or is it the eyelid? Okay, and we're really concerned with B and C, tear breakup and not tear breakup. So we trained, or our team trained this model and then tested it, and all in total used over 50,000 of these image patches. And yes, the training was done by hand. So we were able to classify tear film breakup with an accuracy of 93% and non-tear film breakup with an accuracy of 96%. That's really good. Okay, so we have a big thumbs up for being able to automate where breakup is, automatically find it. And then what do we do that relates to what I do? I fit data with models. So we can take a result of running the program on a trial. And so here it has identified 12 breakup regions. I bet you'll notice there are some others in here. It doesn't get all of the ones that your eye picks all the time, but that's because we asked it to choose regions where there was greater than a 99% probability of breakup. Okay, so we have a pretty strict and high threshold here. What we can do is we can take the data from the center of a breakup region, and then I have simplified versions of the models that I described earlier that capture some of the same effects, and we can fit that data with those models. They are able to capture both evaporation and Marangoni flow, okay? And this procedure is significantly faster to do this fitting and analysis than with the models that I was working with earlier. So I've been working on this project for 3.5 years or so now, and with the very complicated models from the results that I showed earlier, I have done a sum total of 20 successful fits. So that is not a lot of data overall. We're looking to look at many, many images. Okay? So that's our goal. We want to run this process over lots of images. We have over 500 trials, right? 500 videos of people's eyes that we can look at and analyze breakup in. And then if we get a large amount of information, we can get statistics on that, right? And that might be helpful moving forward to compare, again, with our main motivation of dry eye syndrome patients. Okay, so let me wrap up here and remind you what we've been able to do with math. The first thing is we can determine the mechanism causing breakup in certain instances. Okay? We can either say, is it evaporation? Is it the Marangoni effect? Sometimes it's a combination. We can estimate related breakup parameters that can't currently be measured by optometrists, like the salt level of your eye. And in the future, I've mentioned this before, this could be extended, the same idea, to dry eye data, and potentially in the future be a tool for use in doctors' offices. And finally, what I've motivated at the end, we've got an ongoing project using machine learning, and we have automated a lot of the tear film breakup, and now we are going to work on fitting with these simplified models in order to try and get statistical information, generate a lot of fits, get a lot of information, and then again, compare it perhaps to data from people with dry eye syndrome. So hopefully I've showed you a little bit about what you can do with math in a real world application. So I'll thank you for your time.